Hi everyone, happy to be here. So I'll be talking about the small language models and how to ship them on Edge and what we have done to productize them at Microsoft. So I work at Applied Sciences Group at Microsoft, live in Belgrade. Before that, I was also improving speech recognition and NLU at the voice assistant team at Yandex. And so the plan for today is just to give a brief overview on the on-device language models, small language models. The just mark the problem statement, which constraints do we have with respect to hardware, then what we have done in order to optimize the models to run on edge, on device, and then we will cover the let's say capabilities which we have built on top of the foundational model and how we achieved the good performance and quality. So at Microsoft, we have Copilot plus PC devices. Actually, these are some sort of the AI-powered laptops which have the additional chip in them called the NPU or Neural Processing Unit. And so this chip is, let's say, a very, very small unit which is able to run AI workloads on it. At the same time, it saves a lot of power, so it can work on battery. But at the same time, it is also much slower than the GPU, which gives us a constraint on the compute. And Phisilica is the model, which is our kind of frontier on device model. It is 500x smaller than GPT-4, which already gives us the presumption that probably the quality of it will be suffering compared to a cloud model. And so let's try to do our best to make sure it works well. And here's on the stage Satya, our CEO, who is presenting Phisilica, on which I work on at Microsoft Build 24. And so together with Phisilica, we ship some skills such as Rewrite, which is a publicly available paraphrasing tool. So what it does, you have the windows and you select any text on any so-called textual surface, whether it's Notepad or the browser, and then you are offered to rewrite the text in some of the flavors or tones, like formal rewrite, casual, concise, and so on. Another use case of these on-device language models is the summarization of email threads. You have the Outlook, an email client, or some sort of the long list of emails in the thread, and we try to sum it up into several key points by leveraging the capabilities of Phisilica. And so let's get to the kind of first major step we have done. So we have the Phi models family at Microsoft, which is kind of constantly progressing. We currently have Phi 4 series, but Phisilica is based on Phi 3.5, which is a publicly available checkpoint on Hugging Face. So it is a floating point models, and we have taken it and then applied the quantization in order to run it on the NPU fast. And so we have applied, for the quantization, we have applied the method called Quarot, which stands for quantization with rotations. So this method actually introduces a bunch of additional weights for the model, which are basically the Hadamard matrices. The matrices which are giving us the computational invariance. In other words, we try to plug in some additional matrices into the model graph such that we can reduce the amount of outliers and hence our quantization will be better, but also achieve the same kind of input-output mapping compared to the before applying these Hadamard transformations. And here's the example. Before Quarot and with Quarot, throughout the hidden dimension of Phisilica, we see that the spikes or the outliers have been removed, which means that after applying quantization, we will have a much less quality loss compared to before Quarot. And here's how it looks like. Basically, it's just the some feed-forward network layer in which we are just plugging in this Q matrix in several pieces, in several places, so that actually the multiplication of Q and Q transposed is identity matrix, so that it guarantees us the computational invariance. So after we have quantized the model, we managed to run it on the NPU. And I also forgot to mention that basically those neural processing units are provided by other companies which are our partners, and they're building these chips, such as Intel, Qualcomm, and AMD. So we have to run Phisilica on multiple platforms simultaneously. And let's say we are orchestrating this inference with an X runtime. So we have an X runtime layer, and under the hood, for this ONX runtime, we have some execution providers, which are basically some kernels which compute the attentions, feed-forward layers, and so on, specifically for these particular chips on from Qualcomm, NVIDIA, Intel, and AMD. And so after we have managed to run it on all three platforms, we started seeing pretty low throughput. And it happens because NPU, as I said before, is much less computationally productive compared to GPU. So we have to figure out how to increase the throughput or the speed of the generation in our on-device language model. And so we applied the speculative decoding. Speculative decoding is a well-known approach. Basically, what we are doing, we are saying, all right, we have the target LLM, which is here on the left. We completely freeze it. We do not change its weights. But at the same time, we introduce a very small model, which we call the draft model. And this draft model is small because we need to run the end-to-end inference of this model pretty fast. And we try to tune this model to behave exactly as the target model, or PhySilica in this case. And so the draft model is trainable. We train it. And after it is trained to speculate kind of the behavior of the PhySilica, we attach them together, we compile them into an NX runtime and run them all together. And what we are doing, we are trying during the generation, take, let's say, several steps of next tokens generated by the draft model and only one generated by the target model of PhySilica. And then if the first token of the sequence generated by draft is the same as the only token generated by PhySilica itself, if they match, then we accept the whole sequence of the draft token. Thus, we can save the amount of end-to-end inferences, end-to-end kind of next token generations by kind of relying on the speculation from the draft model. Here, how it looks like. So, for example, we have this sequence of generated tokens like hello, Ken. Then we are saying, all right, we need to apply the drafting. So we are generating the token I, and then we have this beam search where we have multiple possible sequences according to the probabilities. And then these green tokens correspond to the draft model. And so the most probable sequences I help you today. And if PhySilica also generated the first token I, then we say, all right, we accept the whole sequence I help you today from the draft model, and we do not run PhySilica on 3 iterations. And on the right side of the slide, there is a kind of real world example when we ran, we prompted the model to write a song about Belgrade, and it has produced some poem, and we see the green tokens which correspond to these accepted draft sequences, and then we computed the compression rate, or how many tokens were generated by the draft model divided by the whole kind of generated sequence. And so we saved almost twice of the compute by applying speculative decoding. Now, it was important also to see like how do we speed up the generation. So for the performance measurements, we are using exactly the same metrics as everyone else uses in LLMs. So time to first token and throughput. In time to first token, we actually didn't change much. So because speculative decoding is intended to improve the throughput. And in throughput, especially for smaller sequences like up to 2000 of tokens on the right side, you can see that we have significantly bumped the number of tokens per second we are generating with speculative decoding, the orange plot. And so it helped us then to move and generate and provide the next thing. Next thing is the text intelligence platform. So after we achieved a good performance and a good quality on device for the PhySilica itself, the question arose like how to make the usefulness for the business. Actually, how can Microsoft benefit from us having this on-device AI, edge AI in Copilot Plus PCs? So we have started shipping text intelligence, which is a set of textual scenarios. Each scenario is basically, let's say, some text in, text out capability, which does some sort of the transformation of the text. So there is summarization, there is rewriting or paraphrasing, and there is also text to table. We have translation and things like that. So in this image, you see that beside the Phi Silica, we have other base models as well. I'm not focusing on them in this talk, but actually that's true. We can use multiple models such as open source Qwen on the NPU, or Mu, which is the encoder-decoder model tuned specifically for Windows settings. So that model, basically what it does, when one types in Windows settings how to increase the brightness of my display, it finds the proper button for that. And so since it's an encoder-decoder model, it's not sufficient to do the summarization and rewriting. That's why we are sticking to Phi Silica for those tasks. And for every skill, we have some sort of flavors. Like for rewriting, we have auto rewrite, casual, formal, and concise. Each flavor is basically parameterized either by the prompt. It can be both hard prompt and the soft prompt, or the LoRa adapter. And we will cover all of those adapters a bit later. And then after we are confident in the quality of those flavors and skills, we are shipping them for our customers, consumers, who could be either the first party, such as Outlook or Microsoft 365 or Microsoft Office, basically other teams within the Microsoft, but also it is available for every Copilot plus PC app developers. Actually, folks who are building .NET apps on Windows, they can trigger these text intelligence skills within their apps through the SDK, which is also useful for developer community. And so we started experimenting with hard prompts and soft prompts first. So hard prompts are basically these textual sequences which we are plugging in into the system message. We try to guarantee that Phi Silica produces reliable outputs for summarization and rewriting, though it is not as easy as for large language models, which are available in the cloud, not these frontier ones, but Phi Silica actually hallucinates a lot. And so we have to be careful about this hard prompt engineering. And so we didn't manage, for example, to be 100% sure that we do not hallucinate when we are doing the formal rewrite, for example. That's why we started exploring other adapters for our TI skills, text intelligence skills. And we found that, for example, Hugging Face provides a very good framework called PEFT, which stands for Parameter Efficient Fine-Tuning. And parameter efficient fine-tuning gives us soft prompts. Basically, those are kind of trainable matrices, a set of virtual tokens, which are, let's say, some sort of extension or superset of hard prompts. And it is done either through prefix token tuning, where we can embed this sequence of virtual tokens inside the user input, or like prompt tuning, which is kind of this virtual token sequence is prependent to the user input. In other words, it's some sort of the system message, but which is trainable. And we experimented with both. So our kind of V1, V0 versions of our text intelligence skills were based on prompts, but then we moved on with LoRa's. So I believe most of the audience know what LoRa is. Basically, it stands for low rank adaptation. And for each layer within Phi Silica, we just attach two kind of matrices, which kind of give us some delta in the activations computation. And given that on this image you see that R is a small value, the total amount of parameters is much smaller compared to these blue pre-trained weights. And that means basically that we can change substantially the behavior of the base model by tuning these orange weights of LoRa and not introduce much of the kind of burden for fine tuning, because the number of parameters for LoRa is negligible compared to the base model. We started experimenting with LoRa, but to do the proper training, we need to collect some data. Unfortunately, we are not able to leverage some data annotation systems such as Toloka or Amazon Mechanical Turk. I believe that Microsoft Azure also provides some sort of this service. And but on the other hand, for small language models, we don't even need such a service. We can just rely on the distillation from the cloud model, because we know that cloud model is 100% better than Phi Silica, because Phi Silica is very, very small. And so we leveraged the Azure OpenAI API to get the synthetics. and we use the distillable library for that. So we have some sort of the pipeline which does the following. It first, like, let's say, filters some input seed data, then it augments the inputs so that we have the kind of the distribution of inputs such that it aligns with the real world telemetry for rewriting, summarizing, and so on. Then we have some additional filtering after we produce the rewritten texts or summarized texts by the Azure OpenAI API. And then it is all orchestrated thanks to this distillable library. Distillable is currently a part of the Hugging Face ecosystem, so there is a good integration with all the transformers, datasets, and so on. And finally, it is kind of a pipeline of some smaller building blocks such as this filtering, augmentation, translation, rewriting, and so on, so that we can reuse it between different text intelligence skills, data generation. And then, yeah, here's how it looks like. Thanks to Distillable, we managed to get the pretty kind of horizontal load on the Azure OpenAI API. So basically, this is the screenshot from Azure Monitoring, where we see how many tokens per minute do we consume from the GPT-4o, which we were using as the teacher model. And so it is very important because usually we don't want to consume too much and, let's say, then filter out everything. So we have to balance the load, then validate the data in the process of its being generated, that we didn't make any bug in our generation pipeline. So this label gives us this functionality. After we have generated the data, we ran the fine-tuning for LoRa. How does that fine-tuning works? We just take the Phisilica checkpoint, put it to the GPU in the cloud, attach the LoRa, then we freeze these Phisilica weights. We change the weights of the LoRa, and thanks to these synthetically generated data. And after that, we have produced the adapter, which we can then put on the NPU and evaluate. But for the evaluation, we had to design a set of metrics. So we used two, basically, let's say, subsets of metrics. The one is a LM as a judge. We leveraged exactly the same GPT-4 endpoint on Azure OpenAI API. And it helped us to evaluate basically some more complex linguistic capabilities, such as for rewriting, it's important to measure the semantic similarity between the source text and the rewritten text so that we do not omit any important information from the input. But we know that LM as a judge is not a perfect way to evaluate the skill because they can be the metrics themselves can be biased by the model and how it was trained. So we also complete our evaluation suite by adding other measures such as BART score. And so BART is the encoder-decoder model, which was released, I guess, in either 2017, 2018. So it is pretty small, it's easy to fine-tune. And basically, after we fine-tune it on the same synthetic data we used for LoRa's, we are simulating the scores of this BART are simulating the negative log likelihood of whether these two texts are kind of correspond to whether the first one is source and another one is rewritten or not. And it is a very good measure in addition to LM as a judge. Also, we are using more classical natural language processing metrics such as lexical richness, some blue and rouge for as n-gram based metrics, just for the sake of the completeness of the evaluation suite. And so let me maybe speed up a bit. So we have made some evals of against the cloud versions. We have a lot of colleagues who are building similar capabilities, but for cloud models. So they're using Copilot, and Copilot has the integration to Word and Outlook and other places. And obviously, those skills are much more kind of they're stronger than ours because they under the hood they're using OpenAI models. And so we have found that we have only 5% of the quality gap with those LLM-based skills, which is, I think, great because the size of the model is 1,000 times smaller. And here's just some examples of these skills and the tones for rewriting. For example, the input is sort of something about Budapest, and for the casual tone it says most stunning cities, and even for locals. But for formal tone, instead of saying if you live there, it's who reside within its borders, which sounds a bit more kind of professional and so on. And then we moved on. So we decided, okay, we have the good skills for the languages which are supported by Phisilica. And the important property of small language models is that they cannot take as many languages in them as we want because of their volume. And so we want at the same time to make sure text intelligence works for languages which are not supported by Phisilica. And we tried the Serbian language experiment for that. Why Serbian is because most of the team are Serbian natives, and it would be easy to eyeball the results. And so what we have done, we translated the whole synthetic corpora for English rewrite into Serbian, and we managed then to tune the LoRa adapter and to see that Serbian LoRa is behaving better than the hard-prom based solution for Chinese, Japanese, and even German, which are supported by Phisilica. It was a good proof of concept, and after that we started productizing this LoRa phone for non-supported languages. Just quick note about how we also contribute to the dev ecosystem. So we think it is very important to hear the third-party feedback on our skills. That's why we expose all the ML infrastructure we are using to text intelligence to third parties. So basically, anyone who has this Copilot plus PC NPU powered laptop can use this AI toolkit extension for Visual Studio Code, fine-tune their LoRa, attach it to Phisilica, and expect some sort of the decent quality based on the quality of the training data for sure. And it should be done pretty easily without a lot of compute, because these LoRa's are less than 1% of Phisilica parameters. And we also have the AI Dev Gallery app for people who are not very much into ML but want to just to see if these capabilities are sufficient for their .NET apps on Windows. Then they can just take this AI Dev Gallery app and see how this rewriting works on device. And here is just some example where I open this task manager, and basically we see the load on the NPU simultaneously to when we are producing these rewritten texts in AI Dev Gallery app. One last thing is the further challenges. So we are going to expand the TI functionalities feature set. So we will do the rewrite parameterization when we would like to control, apart from the tones of like formal, casual, concise, we would like also to support the length control. Like let's rewrite, but make a bit shorter or longer. Then, as I mentioned, thanks to this proof of concept for Serbian, we will be expanding the set of supported languages in text intelligence, which is an ongoing work, as well as we will continue the integration across both the Microsoft ecosystem and Windows App SDK, so that even third parties can leverage the best of Phisilica. And kudos to the team. It wouldn't be possible without all the folks mentioned here and the whole applied sciences group at Microsoft. Thank you.